I'd like to introduce our next speaker, Andrew El-Kadi. Andrew El-Kadi is a research engineer at Google DeepMind, working on the weather effort within DeepMind. He completed his MEng in mathematics and computer science at Imperial College London in 2023, where he focused on quantum algorithms for satisfiability problems. His current work focuses on scaling operationalizing ML for weather models. Please join me in welcoming Andrew. Thank you.
Sabah al-khair. Can you all hear me fine? Awesome, great, okay. So for those of you that were at MenaML last year, you sort of heard the precursor to this talk. So I'm going to do a bit of a recap at the beginning. So for those of you that were here last year, sorry, some of it might sound a bit familiar, but I hope that means you have some good questions for me at the end. And then at the second half of the talk, I want to focus on a specific thing that we've worked on over the past year, and that is cyclone forecasting, or asiyat for those of you that speak Arabic, and how we've managed to transform our models to really focus on this task that's really important and affects a lot of human lives. Okay, so let's take a step back. When I tell people that I work on cyclone forecasting, usually the first question is something like, why do you do that? Or why does DeepMind do that? And the reality is that it wasn't something that we aimed to work on from the very beginning, but rather it's like a natural consequence of the type of work that we've been focusing on around the topic of AI for weather forecasting. And so taking a bit of a step back, let's start by introducing what it means to do AI for weather forecasting, or specifically what my team has been focusing on. And then I'll show you how that eventually translated into AI for cyclone forecasting. So what is, in our case, the weather forecasting we focus on? Well, it's what we call medium range global weather forecasting. Medium range means predicting the state of the atmosphere, so the weather everywhere on Earth, up to 15 days into the future, that's the medium part. Everywhere on Earth, that's the global part. And for multiple variables. So what do I mean by a weather variable? I mean things like the following. On the bottom left, I've got a forecast of surface wind speed. That's how the wind is evolving over the whole planet in time for those 15 days. In the middle, that's surface temperature. And on the very right, that's humidity. And it's not to say that our team was the first to really explore AI for weather forecasting. The field has been really interested in this question over the last few years, and there's been a number of approaches on it. You've got things from CNNs to GNNs, and most recently transformers, which I'm sure you're all already familiar with and have heard a lot about this past week. Okay, so specifically at DeepMind, I work on the weather effort, and there's three seminal pieces of work that we've contributed to. The first is GraphCast. This was a paper we published in Science back in 2022, so right before I joined the team. So I'm not going to take credit for that one. GenCast was our first probabilistic model, and I'll explain what the word probabilistic means in a moment. And that came out in about 2024. And then finally, FGN, and this is our most recent paper and one that I've contributed to the most. Stands for Functional Generative Networks. Again, a probabilistic model, and we'll focus on that again in a second. Okay, so GraphCast and GenCast, really to speed through it, because again, those of you that were here last year, I spent about 30 minutes talking specifically about this topic. So, oh, sorry, that's not sure what happened there. Okay, so GraphCast really in a simple summary sentence is a learned simulator for the weather based on GNNs. And the simulation here is really just simulating how the Earth's atmosphere evolves over time. And GNNs, graph neural networks, for those of you that aren't familiar with them, are really just networks that learn relationships. Relationships between entities, which we sometimes call nodes, and the edges between them corresponding to the relationships. So in our case, the nodes are points on the surface of the Earth, or on the atmosphere of the Earth, and the relationships is how they affect each other in terms of the weather. How does heat dissipate? How does wind impact another region on the planet? So in GraphCast's case, it really boils down to quite a simple process. You take the input, which is the current state of the weather on the Earth, you pass it through GraphCast, and out pops a prediction of what the weather is going to be in 6 hours' time. And that's exactly how GraphCast predicts the weather. And it does so in 3 stages. The first is what we call an encode. The encoding is, okay, we have this representation of the Earth that is in the top left. It's this gridded data of atmosphere weather. And we'd like to encode it to something that we know more faithfully represents the Earth. And what that is specifically what we call a multi-mesh. It's a mesh that's very close to being a sphere, where exactly as I've said, every node corresponds to a point on the Earth. And then GraphCast processes. And processing here is exactly this idea of learning relationships on this graph. GraphCast figures out, okay, this node is impacting that node because it was hot here and then it was cold there, so the heat dissipated. And you can imagine this is happening around 42,000 nodes on this sphere, and GraphCast is learning these relationships through the processing part. And finally, it decodes. It decodes back up to what the input data looks like, these wind and temperature variables and so on, and that corresponds to a prediction 6 hours into the future. And finally, to get a forecast out to the medium range, we just rolled GraphCast out on itself. So GraphCast made a prediction 6 hours into the future. I'll take that, feed it back in as an input, and then get the next 6 hours. That's how I'm at plus 12, plus 18, 24, all the way out to the medium range. Okay, and then in terms of training GraphCast, that's a very ugly formula, so I'm going to start by just blurring out maybe the less important part of it. I really want you to focus on one thing. And the one thing is that the loss function which we use to train GraphCast boils down to a deterministic squared error. We're literally saying, GraphCast, what did you predict? I'm going to subtract away what actually happened, and that's what I'm going to compute the loss on. And importantly, what that means is that GraphCast is only ever asked to produce its best guess of what the weather is going to be. And if that guess is good, it gets a low loss. If that guess is bad, it loses, or it gets penalized. And we repeat the learning process. And that's problematic. That's problematic because then we lose a bunch of information. We have no notion of GraphCast's uncertainty. I don't know whether it was confident or not in its forecast. We have no notion of probabilities or statistics. And the worst thing about this is that we don't get a model that gives us information about the extremes. And in particular, when I say extremes, I mean like events that are very unlikely to occur. And the reason for that is that if you think about what it means to get penalized on a deterministic error, the best way to win at that game is to play it safe, is to produce what we call a blurry forecast, one that's not trying to make too many big claims about what the weather might be. And in a moment, I'll show you what a blurry forecast looks like. And as the name suggests, it's quite blurry. You can tell that GraphCast is playing it safe, and it's not trying to make too many smart guesses about the weather. So instead, we'd like a probabilistic setup. We want to capture these uncertainties, these statistics, and these extremes. And that's why we move to the idea of ensemble weather forecasting. In an ensemble weather forecast, we start with the same input state, but instead of just asking the model to make one prediction, forwards in time, we ask it to make multiple predictions, again and again and again. And from this, we can construct our empirical distribution of what the model thinks is going to happen with the weather in the future, including how uncertain it is and how confident it is about its forecast. So GenCast, which I spoke about a lot last year, was our first approach at this. And it's what we call a diffusion model. The idea, or specifically a conditional diffusion model, is to learn some distribution of X conditioned on some Y. And I promise you, I'm hoping the math doesn't get more complicated than this in this presentation. So a lot of you have probably been playing around with diffusion image models. I think Ruba spoke a bunch about them earlier in the week. In that case, X is an image and Y is text, conditioned on the user asking for something. An example, a photo of a cute dog. The X that pops out is hopefully a photo of a cute dog. And the popping out is what we call the denoising process. You start with some random noise, and then the diffusion process is exactly to denoise this to the final image conditioned on some input. So weather is not too different, or at least in the GenCast setup, our X was the future weather, and our Y, the conditioning, was the current state of the weather. So instead of asking for a cute dog, I've said, given what the current weather is, please denoise what the future weather is going to be. And you can see sort of an animation of what this looks like on the right. And then you can imagine the way that we make the ensemble members is we just start from a different sample of random noise. And each of those samples gives us a different weather model, or a weather sample of the future. And so I thought I told you I'd show you what it looked like when a forecast was blurry. And this is one of my favorite slides in any of the talks that I give because I think it really shows you the difference between a deterministic and a probabilistic forecast. So what we're looking at here is a forecast of a variable called specific humidity, which I'm sure many of you, or the idea of humidity you're familiar with. And it's for a specific point in time back in 2018, on the 20th of September. And I've just chosen a region of the Earth that happens to be where we all are right now, or covers where we are right now. Okay, so I'm going to look at 3 example forecasts. A forecast that started 12 hours before, so I've just asked the model, tell me what's going to happen in 12 hours' time. A forecast that started 5 days before, so on the 15th of September, I said, tell me what it's going to be like on the 20th. and a forecast that started 10 days before. So each of those are from further back into the future, so you'd expect the forecast is going to be a bit more uncertain the further back in time I'm asking it to predict from. Okay, let's look at GraphCast. So 12 hours before, okay, it makes a pretty good forecast. I hope you can see that that frame looks quite similar to what actually happened on the 20th of September. But then the forecast from 5 and 10 days before, I hope you can see what I mean by the blurriness. In specific, look at the bottom left of the forecast from 10 days earlier. That's quite a blurred thing. It looks like someone took some mayonnaise and really, smeared it across the bottom of the screen. And the reality is that that's because GraphCast is uncertain. But the only way it can show me it's uncertain is to go for a blurry guess, just to really smooth things out and play it safe. Let's look at GenCast. Okay, 12 hours earlier, hopefully you see there's a bit of an animation and each of those frames are moving. The reality is the model's confident. It's producing ensemble members that all look very similar to each other. And that's why the animation doesn't look like it's moving that much. But now 5 and 10 days earlier, I'm still getting sharp realizations and ensemble members. None of them are blurry, and hopefully side by side you can now really see the difference. But there is quite a high variance between them. And that's because now I've actually given GenCast a way to express its uncertainty. It does so via these ensemble members all looking quite different to each other. And if I still wanted like a single sample to represent the best guess of the weather in the future, I can just take the ensemble mean. And hopefully you can now see that that ensemble mean goes back to looking a little bit like GraphCast. Okay, long story short, GraphCast and GenCast were both state-of-the-art for their time. So GraphCast beat the best sort of numerical deterministic model called HRES, and GenCast beat the best ensemble numerical model called ENS. And in GenCast's case, we evaluate, or in general on these probabilistic models, we evaluate them in the weather field on a metric called CRPS, the Continuous Ranked Probability Score. I'm not going to put up an ugly formula now. I will in a couple of slides. But for now, just an intuitive sense of what that metric really looks at is it's comparing the distribution of these ensemble members, from them I can derive some empirical distribution, to what actually happened. And if you think about the distribution of what actually happened, well, there was only one thing. So it's a step function. And I'm just looking at the difference between these. How far away was that prediction from what actually happened? And here on the left is what we call a scorecard. A scorecard simply breaks down for every weather variable, so wind, humidity, geopotential, and temperature, and for specific points forwards into time, so from 1 day away, 2 days away, 15 days away, and specific elevations. That's the sort of y-axis on those boxes, how high above the surface of the Earth, how much better is one model than the other. And so everywhere this square is blue, GenCast is better, and everywhere the square is red, the baseline ENS is better. And, luckily, there's not a lot of red, otherwise I probably wouldn't have put this slide up. So at the time we beat them. Okay, but then came along our most recent model, and what I'm going to focus on for the second half, and what we ended up using to do our cyclone forecasting. And they're called functional generative networks, or FGN for short. The motivation for FGN is there's a couple of problems with diffusion. The first thing is diffusion is expensive. And for those of you that work with diffusion, you'll understand that this idea of having to denoise from some random noise is really expensive. It's multiple forward passes of your network. And in the case of GenCast, we needed 40 denoising steps to start from noise and to get a weather forecast. That's 40 forward passes of our whole network every single time. FGN, we managed to reduce this by 8 times. So FGN can generate an entire 15-day weather forecast in 1 minute. And the second is this idea in machine learning, in a very hand-wavy sense of you get what you train for. And ultimately, we evaluate these models on the CRPS. And so the idea in FGN is, okay, well, let's just train FGN on the CRPS directly. And that's not something you can do in a diffusion setup when you're looking at a denoising algorithm to train your model. And by training it on the CRPS, we get a model that not only is 8 times faster, but doubles the improvement on top of ENS of how much better it is. So you have ENS, GenCast improves, and FGN doubles that improvement to how much better it is. So you've got a cheaper and a better model. And I said I'd show you the ugly formula in a couple of slides. I'll show you a way of rewriting the CRPS metric, and I'd like to do this to just give you a bit of intuition of why this is such an intuitive thing to train on. So I said, okay, it's the difference in the distribution. It's the forecast should match the observed outcome. But we can break it down into these 2 following terms. One is the error of the forecast, and the second is the variance of the forecast, or what you can think of as how confident or uncertain the model is. And what we're basically saying to FGN with this loss function is, okay, either you get a low error, so your expected value of x minus y is low, or if you're going to get a high error, you better do that with a pretty high variance. You better show me that you're unconfident in the forecast you're making. Because then at least, even though you were wrong, I knew you expected to be wrong. And that's what we call a calibration. And that's really what we're trying to aim for. We're not just asking a model to be perfectly right, because we understand that that's not always going to happen. We're saying to it, if you're not right, you should at least have indicated to me that you didn't think you were going to be right. Or we say the deviation should come with some uncertainty, should be commensurate with it. Okay, so I've told you a lot about the motivation. How do they actually work? Let's work backwards. So the inference of FGN works as follows. We take a single input sample. This is the current state of the weather on Earth. And we provide what we call a noise injection. And this is a noise vector, which I'll chat about a little more in a second, that along with this single input sample, we're going to inject into the model. And out from that, we get a single ensemble member. Okay, now to generate the other ensemble members, it's pretty simple. I just take more noise vectors with the same input state, and from this, I generate more ensemble members. And voila. And okay, that might sound a bit too simple. Really, the magic of it comes in how we do this noise injection. Two important things about the noise injection. The first is, it's a very low dimensional noise. It's literally a vector of size 32 of Gaussian noise in it. And if you compare that to the dimensionality of the weather system that is on Earth, that's tiny. The dimensionality of weather is like in the order of millions to be hand wavy. Think about the spatial and the temporal and all the variable elements in the distribution that we're trying to learn. And the second is how we do this injection. If any of you are familiar, it's called adaptive instance normalization. Very long story short, in our network, we have these layers called layer norms, and they normalize the outputs of layers in the network. And what we're literally doing is we're injecting noise into those layers. So the noise is being injected into the weights and parameters of the model, not into the inputs of the model, which is usually how people do noise injection. And we find that this is exactly what manages to construct these accurate and coherent weather states. It's the parameter-based injection as opposed to the input space injection. And we say that this is what allows the model to capture aleatoric uncertainty, if any of you are familiar with that term. Okay, and then for those of you that are familiar with ideas of uncertainty, there's a second type of uncertainty, and this is what we call the epistemic uncertainty. And this is just uncertainty that comes from the fact that we don't have an infinite amount of data. We also don't have a perfect learning algorithm, as much as we'd like to think that that's what we've made at DeepMind. And so the way we counter this is, again, with this is a very traditional technique that I'm sure many of you have come across, and I've spoken to many of you about with your posters here in the last week. It's model ensembling. So what you're looking at here are 4 copies of the same FGN setup, but each of them were trained separately using a different seed or noise during training. And then we just repeat this process on a per model seed basis. So model 1 gives me, let's say, 4 samples. Then model 2 in green gives me the next 4 samples, and so on. And from that, I've got my 16 ensemble members. Annoyingly, we use the word ensemble twice here. I have 16 ensemble forecasts that came from 4 models in the model ensemble. And so hopefully you can see this is just a copy of that process I described on the previous page. And in terms of training, actually training FGN is pretty simple. We do exactly what I just described. We just slap on a CRPS loss function to it. So I take my single input sample and this noise injection that I just described, and I use that to generate 1 sample during training. I do the same thing again to get my second sample during training, and then I just impose the CRPS loss. And that's literally how we train FGN. And the reason this works, and you might think, wait, you're using 2 samples, is that really enough to get a distribution? Is that the CRPS is an unbiased estimator. And so it's really enough to just compute this unbiased fair estimator from 2 samples to train the entire model. And then obviously at inference time, I can just inject as much noise as I want and get as many ensemble members as I want. And that's what happens. So just to give you a bit of a taste of the architecture, super similar to what I described with GraphCast, except we swap out the middle. Instead of being this GNN, it's a transformer. Happy to answer any questions about that later. And we do the same thing with this autoregressive rollout. I take my input, FGN gives me a bunch of samples, I take those samples, and I get my next 6-hour prediction. And I roll that out autoregressively to go all the way out to 15 days into the future. And as I said, the good news is that FGN is better than GenCast. So this is another CRPS scorecard of how much better FGN is than GenCast. And a few slides ago, I showed you a scorecard of how much better GenCast was than ENS. And so it's blue on blue. What's also nice is we see these really promising joint structures. And so if you go and read the FGN paper, which is about 100 pages long, so you can choose whether or not you want to do that. I probably haven't read all of it myself. We divide the Earth up into some more of these complex evaluations, into these pooling regions, and we compute some similar metrics. And this really shows that FGN has learned how to construct these coherent trajectories of the weather across space and time. Okay, and so you might have noticed by now I've been talking for about a good 20 minutes and still haven't mentioned cyclones, and so we finally reached the final part of the talk. And I just wanted to give you a bit of context before I dived into the cyclone bit. So for the cyclone, we released a model recently called FNV3, and we're actually running this in real time, and I'll show you in a moment how you can see FNV3 running in real time. So, okay, I explained this whole rollout of FGN. You can imagine that we've got this analysis-based +6, +12, all the way out to, let's say, 4 days, even though FGN does run to 15 days. And usually the way that people do cyclone tracking with weather models is they apply what we call a vortex tracker. And really what this is looking at is a cyclone has a number of properties. It's like there's a lot of wind, a lot of rain, very low pressure, a lot of geopotential energy. And so what this vortex tracker literally does is it looks for these properties. It takes the weather forecast and it says, where is there a region with low pressure and high wind? And from that, you get a bunch of these nodes, and then you stitch the nodes together, and out comes your cyclone path. But there's a number of problems with this. And at a high level, the problems boil down to a bunch of things with underestimating how strong the winds are. And that's to do with the fact that these are global weather models, and so they're quite coarse and don't capture wind that well. The second is the size of the cyclone. We don't just care about how strong the wind is, we care about how much of the region around the cyclone is going to be affected by that wind. And the third is they're quite bad at a topic called rapid intensification, and that's the most dangerous type of cyclone impact. It's when a cyclone looks quite weak and in a very short period of time intensifies rapidly and all of a sudden becomes very strong. And those are the worst when it comes to being able to prepare for the destruction that they're going to bring. So what do we do about this? Well, we take our FGN setup, and this is another example of where FGN becomes more natural to use than a diffusion process. And we fine-tune it along with the normal weather data on specific cyclone data. We take a data set called IB-Trax that goes back to 1979, and from this we have around 40 years of cyclone data, specifically the path the cyclone took and how strong the wind was and where it reached around the cyclone. And there's like a small snippet of what this looks like in the top right. And so alongside this normal task of predicting the rollout of the weather, we also ask FGN to predict specific cyclone locations. And so what this looks like is, at every step, on top of FGN predicting the next state of the weather, it also specifically predicts things about the cyclones. It predicts their latitude and longitude, their wind speed, their pressure, and the extent, how much that wind and where exactly it's touching. And from this now, in order to forecast the cyclone, we do the following. At each step, we get the cyclone direct output prediction of FGN. And from this, we get all of our nodes. And you can see now that we actually do have information on the extent. That's sort of pictorially demonstrated by the size of those circles around the dots. And then we can stitch them together in order to get our cyclone path. And what's amazing about this is that because FGN is so cheap, we can generate so many ensembles. And this is true of all machine learning weather models and one of their benefits over traditional models, but it's especially true of FGN. So here's 2 members, 3 members, 50 members, and actually in real time, we run 1,000-member ensembles of FGN every 6 hours to forecast cyclones everywhere on Earth. And from that 1,000-member ensemble, we can get some really detailed information on the extremes, exactly the problem we set out to solve with GraphCast at the very beginning. In particular, here are some plots we've made. This is of a real cyclone back in 2022, of the probability that the wind exceeds some threshold of strength in the next 4 days. And you can see it really allows us to focus in on which areas are going to be most impacted by the impact of the cyclone. Okay, and luckily, this isn't just a proof of concept. We've actually demonstrated that this model is the state-of-the-art cyclone model. And so here you're looking at the performance of FNV3 on track error, aka how far was the track that it predicted actually from the track that the cyclone followed. Luckily, the blue line is the lowest line. We have the lowest track error. We've also got the state-of-the-art intensity error, and as I said, this is something that ML models really struggled with. They really struggled to capture how strong the wind around cyclones was going to be. And again, the blue line is the lowest line. And finally, the extent error, the size of the cyclone along the path that it follows. Again, the bluest line being the bottom. And so we've really been partnering up with weather agencies, and the National Hurricane Center in the US and a number of agencies around the world are now directly using FNV3 in their official forecasts to disseminate to their citizens. And I just wanted to link that if you go to deepmind.google.com/science/weatherlab, we're actually disseminating all of these forecasts in real time. And in particular, what you see, the blue one, which is our experimental model on the website, corresponds to FNV3. So if you open this up right now, you will see real-time forecasts. You'll also be able to go back and see historical forecasts that we made in the past or would have made if the model had been running at that point in time. So thank you very much. This is work done by a really large team. And in fact, the people that are up on this slide are specifically those that were involved with the Cyclone work. There's also a lot of authors on the GenCast and the GraphCast side. So a shout out to them. And a shout out to you guys for listening. It's been great. Thank you.